So last day we introduced the concept of vectors, looked at vector addition, subtraction, multiplying by a scalar, but not in any kind of system, just in drawn vectors, vectors that are drawn and possibly given a magnitude, and then the direction could be something like true bearing or quadrant bearing or something like that. Again, it's a system that's used certainly in navigation and that sort of thing, but in mathematics it's not super useful. So today is all about building a better system where we can represent vectors with numbers very specifically in a very well-defined way, and starting to look at the operations in that system. I'm not sure I mentioned this in the last video, but a lot of this unit is really just defining new operations, defining new ideas, new terminology, new notation, and really just coming to terms with that. Again, like in the past, that means none of the computational mathematics is challenging. Most of it's very simple and straightforward, but because it's so new, it just takes time getting used to, and remembering all of the different aspects, not getting them mixed up with each other. The other part of it, and we'll see this more starting tomorrow and the following few days, is some of the results of different systems, how we interpret them. That's going to be really important. And again, that's just experience and remembering those results and putting all the pieces together of a very new system, that sort of thing. So keep that in mind when you're working through this material, that a lot of it is just very new, and so it seems tricky that way, but the computational side of it is fairly straightforward. So today we're talking about Cartesian vectors. And Cartesian vectors are vectors that are drawn on the Cartesian plane. And this, like I said before, gives us a really well-defined system whereby we can represent vectors numerically, and it's a well-defined system. And that way, all of these operations that we want to do, we have numbers to represent them that work very well. So first of all, the definition of what a Cartesian vector is a vector in Cartesian space is defined by its tail being at the origin. So its tail will be at 0, 0, and its tip will be at some point, any point on the Cartesian plane, given AB, but we often denote vectors with square brackets as opposed to round brackets. And so I can have some vector okay, and so this point is A, B. So this point that the vector ends at, it starts at the origin and ends at the point AB. And we would define this vector, let's say vector u, as a b. So the point that the vector goes to would be point a comma b with round brackets, but for us, we denote vectors with square brackets. Now there's a few different important ideas here. Remember, we talked about this yesterday, that vectors don't exist in a particular position. So the definition of the notation is when I say some vector AB, by definition, its tail is at the origin. But I could take this vector, and this is something that takes a lot of getting used to. I could take this vector. How long is that vector? About 2.5, and I can move it wherever I want. So I could put it here, for instance. And this would still be vector u. And the only thing that's important about this vector is that the distance, the horizontal distance from tip to tail, is still equal to a, and the vertical distance from tip, or from tail to tip, tip to tail, is b. It doesn't matter where it starts, but we still define the vector as its horizontal distance and its vertical distance. And this seems counterintuitive, I think, that that vectors don't have to start in a particular position. That seems very strange, especially given the training we've had in the past where a function starts, where its y-intercept is very important. But it turns out with the system that we have with vectors, it doesn't matter. Okay, so keep that in mind always, that by definition, when I define a vector as AB, vector AB, it means AB relative to a starting position at the origin, but it doesn't necessarily exist there. It could exist anywhere. You can take it and you can move it. You can think about it wherever you want in space. One final note before we move on to a few more definitions and then looking at some operations is this is not a universal notation. There are definitely people who define vectors this way, and that seems a bit strange only because it looks like an ordered pair, but it tends to be still a system that works fine just based on context. If you know you're talking about a vector, then it means a vector. We don't use that system because we do feel it's a bit clearer where you can define a point compared to a vector, and you can say one is a point and one is a vector just in your notation. So we use square brackets for vectors and round brackets for points, but that's not a universal thing. There are definitely people or disciplines who use round brackets for vectors. And then another really common way of seeing vectors is vertically like this. And this is brand new. If you are running through our matrix unit independently, you could view this as a matrix. And this is a very common way of expressing vectors, in particular in linear algebra. If you were taking that in university, first year, second year, linear algebra, you're going to see vectors represented like that all the time, although they may not actually even talk about them as vectors. They may just talk about them as matrices. But understanding that this is a representation of a vector, it can be really important. So you see them drawn vertically like this, but we're going to do them horizontally. You see them with round brackets. We're going to do them with square brackets. There's no universal notation, which can be confusing, but once you get a solid understanding of vectors and the way that we handle them in mathematics, moving from one notation to another won't be the hard part of dealing with all of this. Okay, so that is the very most important fundamental introduction of what a Cartesian vector is, how it's defined. Another really important definition, something that we'll use a little bit, and again, this is just notation, this is just definition stuff. In linear algebra, this is really important. For us, it's less important, but there will be, questions here or there that just make sure that we understand these definitions. And it is unit vectors. So the unit vectors in two space are defined as I hat and j hat. That's what we call them. And they are vectors that are perpendicular to the x-axis and the y-axis respectively. So unit vector means it's a vector with a magnitude of 1, right? So we talked about magnitude. That's like the length of the vector, the length of the line. And vectors, again, have two properties. They have length, they have magnitude, and then they also have direction. And in two space, their direction can be any of the 360 degrees. And their magnitude obviously can have anything. It can be positive, it can be negative, all sorts of things. Well, magnitudes by definition aren't negative, but it can be one direction or the opposite direction, right? And so we have these special unit vectors, I hat and j hat, that run along the x-axis and the y-axis. So I hat is along the x-axis. So this is I hat. And j hat runs along the vertical axis, the y-axis. So this is j hat. And so because of that, by definition, I hat equals 1, 0. Just using that notation that we talked about, it has length along the x-axis of 1 and no movement up or down. And j hat, by definition, is 0, 1, and it has length 1, positive 1 up the y-axis, but no movement on the x-axis, so no movement left or right. Okay? And again, this is just notation. This is just by definition. Out of context, you have to remember it always seems strange and it doesn't seem to be meaningful, but this turns out to be an important way of expressing vectors when you start to get into linear algebra and doing some of the computations in a different way that we're not going to see a lot, but we'll start to practice and get used to a little bit just so we're prepared when you move forward with this. Okay? So that means any vector can be expressed in terms of its horizontal and vertical components. So vector AB can be equal to A times I hat plus B times J hat. Now this looks like it's going to be some value, 2 times 3 plus 4 times 5, and you're just going to get 26 as your value. But I hat and J hat are not just variables. They are not just variables that represent a number. They are vectors. So each of these is a scalar times a vector, which gives you a vector. Another scalar times a vector, which gives you a vector. Adding two vectors gives you a vector. So A times I hat plus B times J hat will result in a vector, and it's the vector AB. Okay? And we could break this down as being A times I hat, which is 1, 0, plus B times J hat, which is 0, 1, which is vector A. This is just using scalar multiplication that we looked at previously. Whoops. 0, B. And if I add those together, obviously that's going to give me vector A, B, because 0, A plus 0 and 0 plus B gives you that. So that is, and this step right here looks at your horizontal and vertical components separately. This is useful in physics. You do a lot of that, breaking up vectors into their horizontal and vertical components. I don't think you use this notation too much, but that is something that could certainly happen. Okay, so again, that's just definition. And writing out vectors in terms of I hat and J hat, their horizontal and vertical components, is something that we'll do just to practice that idea in and of itself. Okay, it's not going to be all that helpful for us in this unit, but we're going to do it just to practice. Okay, last thing we'll talk about here, magnitude. So if vector u is AB, then the magnitude of u is the square root of a squared plus b squared. By definition, this is obviously from Pythagorean theorem. Okay, let's draw this out. So I've got some vector, and this is A, and this is B. So vector u in this case is AB. Don't forget, it doesn't have to start at the origin. I could take this vector and move it anywhere, but that's how we define vectors in two space. And so if I think of this as a right triangle, it has a height of B and a length of A. And so I can use Pythagorean theorem. And the magnitude of u becomes the square root of the horizontal component a squared plus vertical component b squared. That's an important definition. It's something that you may have to do a fair bit of to be able to find lengths or magnitudes of vectors in all kinds of different areas. Okay. I think that's that. Now let's look into some operations. So adding Cartesian vectors. When adding vector u and vector v, you just add the horizontal components and you just add the vertical components. I think that this is intuitive. So I think that this is an easy one to make sense of, to come to terms with, but it always is useful to think about why this works. So let's take a look at a couple of vectors. I'm going to do vector u like this. And I'll do vector v like this. And what would happen if I added those? And again, if you think about them both starting at the origin, then it seems strange to understand how you would add them. But remember, vectors don't exist in a position in space. They can be moved around. So let's see about how long this vector is. Okay. It's about 1 unit. So if I take it from here and I move it there, so this is also vector v, then my resultant vector of u plus v becomes, setting them tip to tail, is this vector. And now we can take a look that the horizontal value of u and the horizontal value of v will be the horizontal value of u plus v, right? You can see that when I line them up tip to tail, if I go horizontal for u and then horizontal for v, I get the horizontal for the resultant vector. And same thing, the vertical component of u plus the vertical component of v gives me the vertical component of the resultant vector. So that means that vector u plus vector v is, the x value or the horizontal value of each vector added to give you the x value of the resultant vector, and the x values of the vertical component, the y values, to give you the vertical component of the resultant vector. And then similarly, and you can do the same thing visually with vector u minus vector v, you just subtract the x's and the y's, or the horizontal components and the vertical components. Okay, so very quickly, a specific example: 1 plus 3, 2 plus negative 4 is 2 minus 4. And that gives us the resultant vector of 4, negative 2. Okay, again, quite intuitive. And that's why this is maybe our first indication of there's a specific example how Cartesian vectors are fairly easy to work with. Computationally, the mathematics makes sense, and it's not very difficult, and it gives us good results, good usable results. Okay, what about multiplying a vector by a scalar? That was the other thing that we looked at. So I'm going to draw a vector like this, and I'm going to call it vector u. Oh, that wasn't great. Okay, so here's vector u. And so vector u is 1, 2. So then what would 3 times vector u be? Well, I'm going to go if this was a distance of 1, I'm going to triple that. So 1, 2, 3. So instead I'm going to go this far. And this was a distance of 2, so I'm going to triple that. And instead I'm going to go 6. So I end up going 3, 6. And this is my resultant vector. So again, very intuitive, very straightforward. I just multiply my constant, in this case 3, by each component. And you're going to see, we're going to see that this is really easily scalable. When I go to 3 space or theoretically 4 space, 5 space, you know, these basic functions hold true, where you can just multiply the scalar through and you get a similar kind of result. Okay. Okay, some examples. Given vector u and vector v, find an expression u in terms of its horizontal and vertical components. Okay, so vector u is 3 and negative 5. And remember what this means is 3 times I hat plus negative 5 times j hat. And we don't do a ton of this, so I could see you forgetting what this means. But when it says horizontal and vertical components, it's talking about I hat, j hat. And I hat is 1, 0, so this becomes 3, 0. And j hat is 0, 1, so this becomes 0, negative 5. Seems this, and again, this just seems like something like, why bother? What's the point of this? Well, it turns out this is kind of a fundamental beginning of linear algebra, which is a huge part of mathematics. So it is important, but we won't get into it deep enough to exactly see why. If I wanted to take this example further, it's 3 times I hat, which is 1, 0, plus negative 5 times j hat, which is 0, 1, which gives me that sum, which has a result as a vector. Okay. Express u in terms of the unit vectors. So this is kind of what we already did, almost backwards between these two examples. So u, I just write it as, all this means is 3 I hat minus 5 or plus negative 5 j hat. Okay, so in terms of its horizontal and vertical components, means I'm writing it out like this. In terms of the unit vectors defined as I hat, j hat, we write it like that. So again, this is just notational stuff. It's a lot of new material to remember, but you just have to, practice and get used to it and come back to it and don't do it all in one night, because then you'll just forget. But do it over the course of couple weeks, and hopefully you'll remember all these different little nitpicky things. Okay, what about negative 4 times vector u? So vector u is 3, negative 5, so that's negative 4 times 3, negative 5, which is negative 12, positive 20. So I had a vector that was here, 3, negative 5, 3, negative 5. And now it's negative 12, 20. Right? But you can see that it's a scalar multiple, because you would be able to, if this was drawn perfectly, they are collinear. Those two vectors would be parallel to each other. They're in opposite directions because I multiplied by a negative. Okay, don't get too caught up in all the computations. The visual of this is so important, so always be visualizing. Even a tiny little sketch like this can help us remember the visual aspect of what all this means. 3 times vector u plus 2 times vector v. Again, there's nothing fancy about this question. It's just getting used to the notation, getting used to the different operations that we can do, scalar multiplication, and vector addition. So this is 3 times 3, negative 5. which is vector u, plus 2 times negative 2, 4, which is vector v, which is 9, negative 15, plus negative 4 and 8. And if I really wanted to, I could write this out as 9 minus 4, negative, 15, plus 8, which works out to 5, negative 7. So the scalar multiplication just goes through to both components, just like distributive property. And then adding vectors, I add the horizontal components and I add the vertical components. Again, these are just more examples to get us working with vectors with the notation and just getting used to some of these things. Some of these operations are going to come up over and over again and be very useful. Okay, so the magnitude of u, again, we have a formula, is the square root of 3 squared plus negative 5 all squared, which is square root of 9 plus 25, which is root 34. And often if that were able to be reduced, we would write it in reduced form kind of thing. Okay, and then how about the magnitude of vector u minus vector v? So you could do this kind of all in one step, but I'm going to do it in 2 steps. Vector u minus vector v, okay, is 3, negative 5, minus negative 2, 4, which is 3 minus negative 2 is 3 plus 2, which is 5. And negative 5 minus 4 is negative 9. And then the magnitude of that vector, 5, negative 9, which is vector u minus vector v, is 5 squared plus negative 9 squared, which is 25, the square root of 25 plus 81, which is the square root of 106. Okay, nothing deeper to any of these. There's no deeper understanding, just getting used to the notation, working through the operations, and practicing that sort of thing. Determine a vector in the opposite direction to v. Again, this is a question, G and H are both questions that really are just trying to get us to do different things with vectors and think about all the properties of vectors and understand the different definitions, like what collinear means, what a unit vector is, what opposite direction means. Part of the problem is they have multiple answers. There's no one clear answer. There's an obvious answer to a lot of these, and there's not necessarily just a single answer. So that's tricky for some people, and again, with some practice, you'll come to terms with that. So vector v, I'm just writing it out because I don't have it here, is negative 2, 4. Okay, so any vector in the opposite direction would be something like negative vector v, which is negative 1 times negative 2, 4, which is positive 2, negative 4. It's as easy as that. Again, the actual mechanics here, the actual computation is really simple and straightforward. It's just understanding what the question is asking. And there's nothing about there's nothing given about the magnitude of this vector. So another one could be 4, negative 8, 8, negative 16. I mean, I could come up with all kinds of other vectors that are in the opposite direction. Means they're parallel, but going the other direction, right? So it's not just like generally pointing. So let's take a look. It wouldn't be something like, well, this vector is pointing this way, and this vector is pointing the opposite direction. No. In our general language, that might kind of be opposite-ish directions, but that's not what this means. This one means very strictly opposite. One's going this way, the other one is going directly opposite. The magnitude doesn't matter, so it can be longer or shorter, just that it's in the opposite direction. That's a strict definition. Okay, and what about this? A unit vector collinear. So collinear means parallel. Again, that could be same direction or opposite direction. But if you're thinking of these as lines, they're not lines. They're not the same thing as a line that we look at starting in grade 9. Okay, but there are some parallels between vectors and lines, and this is something that your understanding of lines can actually help you come to terms with vectors a little bit. Thinking about slope and that sort of thing, it actually can be useful as long as you don't take it too far and start to think of them as the same thing, because they're not. So I have two lines that are parallel. That means they're collinear, but it has to have a very particular magnitude because it has to be a unit vector. Okay, so how do we do this? We have vector u, which is 3, -5. And we're going to determine the magnitude of u. There is just a straightforward, simple step for how to do this. We actually already did this, so I'm not going to redo it again. We did it up above in example E. So the magnitude of u is 34. Okay. So in order to find a vector that's collinear, we can multiply by any scalar multiple. So if all I had to do was find a vector that was collinear to u, I could multiply by 2 or 3 or -5 or 10 or 100 or any scalar multiple, multiply it by u, and I would have a different vector that has a different magnitude but is still collinear or parallel to vector u. Okay? But if I want a unit vector, I have to multiply by a particular constant k. And what will work is if I let k equal 1 over the magnitude of the vector. The only trick, and then this will just work every time. So again, there's a straightforward set of steps that will allow you to determine a unit vector that's collinear with u. But the only mistake that people make doing this is they find the magnitude of u and then they change the vector that they're multiplying by. So this is 1 over the magnitude of this vector. So that means I have to use that vector. I can't use some other vector. Okay, I can't perform some other operation on it for it to become some other vector. And you'll see what I mean about this when you do some of the questions that ask you to do some different things. This is what happens. Okay, so this ends up just being 3 over root 34, comma, -5 over root 34. And that is, and will always be, a unit vector that is collinear to vector u. I just divide each component by its magnitude. So you could just memorize those two steps. If you're asked to find a unit vector that's collinear with some vector, you find the magnitude of that exact vector that you're finding a unit vector collinear to. It's got to be that exact vector, find its magnitude, and then just multiply through by the magnitude, right? So it's an easy two-step process. I hope lots of people want to know why. I hope it can be useful to think about why. And then if you ever had to apply this understanding in some other kind of way, you might be able to extend this into different areas. So we'll quickly, but you don't have to know this in order to know what to do. You could just memorize those two steps. But let's take a look, because it is accessible, why this is true. So let's take a look at the magnitude of our constant k, which is 1 over the magnitude of u, times vector u. So it's going to be 3 over root 34 all squared plus -5 over root 34 all squared. Now before we do anything, think about what this is. When I square 34, root 34, and I square root 34, I get 34, right? That's kind of set up that way. So I've got a common denominator of 34. And when I square 3 and when I square -5, I get 9 plus 5, and that was how we found, if I can find it here, 9 plus 25 was how we found the magnitude of vector u. So because of how I've set it up, this will work out to the same value as the magnitude necessarily. I'm going to get 9 plus 25. Okay, so I'm going to write that out. So I get 9 over 34 plus 25 over 34. So my denominator will always be the magnitude, and my numerator will always be that same sum that gave me the magnitude in the first place. So I end up with 34 over 34, root 34 over 34, which is root 1, which equals 1, which means it's a unit vector. So that's why this works. I think it's helpful to think about that and to sort of follow those steps of understanding. But when it comes down to it, finding a unit vector requires 2 steps. Again, all of this seems easy. New notation always seems easy because it is just definitions. It is just notation. There's not really any understanding involved. There's understanding there in why this works, but there's no understanding necessarily in just the notation of something, okay, or the definition of something. It just is that way. So it seems easy at first, but there's all kinds of things that can get mixed up throughout this process. So don't take it too lightly. This is brand new math. It does have its challenges, absolutely, right? In particular, when we start asking more complex questions like find a vector that has these properties, you have to start to apply some of your own understanding, okay? All right, last thing here is determine a unit vector in the opposite direction to vector u. So now it's got to be a unit vector. It's got to be in the opposite direction to vector u. Okay. Well, I already have a unit vector that's collinear to vector u. It's in the same direction as vector u. I've determined that in part h. So for part I can just do -1 times that vector, which is 3 over root 34 and -5 over root 34. And this will be in the opposite direction. I can multiply by any negative scalar. So this is -3 over root 34 and +5 over root 34. But why not make it easy and just make it 1? Then I don't have to do any other mental math. But oh, no, it has to be a unit vector. So actually, I take that back. If I had multiplied by -2, I would have a vector in the opposite direction, but it wouldn't be a unit vector. So in this case, because it's a unit vector, you absolutely have to just multiply by -1. Let's say we weren't asked to find a unit vector collinear with vector u first, and you were just asked to find a unit vector in the opposite direction of vector u. Then you'd have to do this whole process first, and then you'd have to multiply by -1 to get a vector in the opposite direction that's a unit vector, right? So those are the kinds of small twists that we can add to questions where it makes it a little bit trickier. And it is enough that you have to develop your own plan of how you're going to solve the problem that, does take some practice and some familiarity with all of this stuff. Okay, last thing we're going to look at is finding a Cartesian vector between 2 points. And again, this is something that we'll actually do quite a bit of, and it's a simple concept. We're going to look at why this works, but then it's something that you maybe want to just memorize, and it is easy to memorize. There's a tiny little saying that will always work, but you have to understand when you are asked this question or when it's a part of a bigger question, you have to understand what you're being asked very specifically. So keep that in mind, that this is actually a fairly important idea. You need to know what to do, and we're going to look at why it works as well. So P is a point that has coordinates x1, y1, and Q is another point that has coordinates x2, y2. Okay, so let's draw this out first. So here's point P, and here's point Q. I'm just defining these randomly. Okay. So I can draw a vector to P, and I could call it vector A, and I can draw a vector to Q, call that vector B. And so in this case, and we typically define as a standard the origin to be O, point O. So vector A is vector OP, and vector B is vector OQ. What if I want to find the vector between P and Q? So this is something that we will actually do a fair bit of. So here's my vector from P to Q, from point P to point Q. Now this vector's tail is not on the origin, which is fine because vectors don't have to have their tail on the origin. The notational standard is that their tail is on the origin. But how do I figure out how I would describe this vector as if its tail were on the origin? Well, to go from P to Q, I just draw a diagram like we did yesterday when we were doing those diagrams. I just follow along from the start to known coordinates. Whoops. That's not what I meant to do. And if I follow this path from P to O, then O to Q, then I will get the definition of PQ. So PQ equals PO plus OQ. But PO is not a vector that I know, but OP is. And OP is the opposite of PO. So if I do negative OP plus OQ, and then I'm going to swap these around and do OQ minus OP, because that's the same as negative OP plus OQ. This is really important, okay, because this is subtracting backwards. Okay, if I want to go from P to Q, I do OQ minus OP every single time. This is just a formula that will work. But this diagram over here is why this formula works. I don't know PO. I do know OP. And so that allows me to use this pathway that we chose to go from P to Q by doing OQ minus OP. Or you may think of it as like point Q minus point P. Now we're not going to do it that way. We're going to do it in vectors, and that's important, but you could think of it that way. So it's strange to go from P to Q. You subtract Q minus P, but that's how you do it. And Q and OQ is from the origin 0 to Q, which is x2, y2. Now I'm not just writing out the ordered pair because now I'm defining it as a vector. That's a subtle difference. And then x1 comma y1. And this would be x2 minus x1, whoops, comma y2 minus y1. Okay, and that's how I could find a vector defined from P to Q. So this is going to be an important idea. If I wanted to find the magnitude of PQ, again, that's something that we might do. Then I get x2 minus x1 squared plus y2 minus y1 squared, which looks a lot like the formula for length of a line segment from grade 10, and it is obviously similar, related to that idea, same concept, but now we're talking about vectors, so it's interesting how it comes around full circle. Okay, last example here. We're going to find the position vector from A to B, given points A and B. Notice that they are round brackets, that they're given with round brackets, so they're points. But we're going to find vector AB, and we're going to find its magnitude. So to find vector AB, as we just covered, you always subtract backwards. So from OB minus OA. Okay, and OB, it might look like we're just rewriting point B, but we're not, because we're defining it as a vector. So that's an important difference. It's a subtle difference, I know, but it is very important. And then writing this out in its components is -3 minus 2 and 8 minus -5, and that gives us -5 and 13. Oops. Okay. And again, this is a formula. So this is something that you can use every time, do every time, but it is, I mean, it's easy to follow when you look at that diagram that we looked at, but it's, in some ways, it's not intuitive. So this is something that on a test, some people just totally blank and have no idea what they're supposed to do. So they just don't know how to find the position vector AB and either leave a blank or make something up, right? So then to find its magnitude, again, finding magnitudes of vectors is something that happens often enough that we want to be able to do it proficiently, quickly, without having to think through a lot. So just use this formula, square root of each component, of the sum of each component squared, and that works out to 100 and root 194. Okay, so those are some different examples of things that we can do in Cartesian space. This is an important idea, because instead of saying I have a vector that's 34 kilometers long and it is north 53 degrees east, where that's kind of how we were looking at it on the last day. Now we have a defined number system that we can use to represent vectors and to do these operations with. And we're not just drawing vectors and trying to represent their magnitude with the length of a vector. We can define them numerically and do all of these operations. So we're going to see moving forward how important this is, and most of what we do will be with vectors in Cartesian space like this. Okay, but today was really just about the notation and definitions and getting used to it, the different things we can do, again, coming to terms with what magnitude means, what a unit vector is, what collinear means, all these different things, and all these made-up examples that we're asked to do to find a unit vector that's collinear and in the opposite direction of some vector. These are just getting us used to the different operations and these different properties or definitions of vectors. Okay, so that's really, this introduction in Cartesian vectors is really just about getting used to that idea. The work for today isn't every question, so it's just those questions. If you want more practice of some of them, I think it's fine to do the other ones that aren't assigned. Okay.